Section 14.6, tangent planes and differentials. A couple learning goals here. Know how to find equations of tangent planes and be able to estimate functions, values with linear approximations. So to motivate what's going on in this section, I want to spend a little bit of time talking about variable functions. It's always good for us to remember what's the Calc 1 version of all of this stuff so that the Calc 3 version, the multivariable calculus version, will make more sense here. So let me just draw some picture here. Okay, so here is some function, f of x, in one variable. At this particular point here, let's call this point here A. We can think about what is the tangent line. What is an equation for the tangent line to our function at this point? And so the way that we would do that is we need the following pieces of information. So we would need f, so this point here is the point A, comma, f of A. And the slope, of course, will be given by the value of the derivative of our function evaluated at A. So the equation of a tangent line in this case is going to be y minus y naught, the initial point is f of A, is equal to m, the slope, f prime of A times, let me make that prime a little bit bigger there, times x minus A. I can rearrange this maybe into a more familiar form. Y is equal to f of A plus f prime of A times x minus A. So this is the equation of a tangent line. We can also think about this, this giving us equation for a line. This can also give us a linearization. So just the same expression here, just thought of in a different sense. L of x is equal to f of A plus f prime of A times x minus A. If we wanted to go to, like this right here, what do we think, what's our estimate for the value of L of f of A plus 0.01, let's say. F of A plus 0.01 is approximately equal to L of A plus 0.01. So this linearization is a function. We've computed f of A, we've computed f prime of A, plug in A plus 0.01 into our linearization. It gives you some kind of approximation here. Now, of course, the approximation will be better in general when you're closer to A, the point that you're centering your linearization at. Okay, so this is all motivation one variable functions. You all feel very, very familiar. Well, what happens? What happens when we go to two variable functions? So for two variable functions, we aren't going to have we aren't going to think about this in terms of a tangent line. We're going to think about this as a tangent plane. So if we have some, okay, I'm drawing some 3D region here. So here is our 3D surface. We can think of right here, there is some kind of tangent plane that's tangent to our 3D surface that's given by this two variable function, tangent plane. And so what is the equation of the tangent plane? Well, it's basically exactly what we would expect it to be. Z is equal to f of a, b, I guess, let's say here f of x, y is our two variable function. Z is f of a, b plus the x partial derivative evaluated at a, b times x minus a plus the y partial derivative of a, b evaluated, the y partial derivative evaluated ab times y minus b. And so we should, let's just compare these two things really quickly here. That for our equation of the tangent line up here, y is equal to f of a, the original function value. Z is equal to f of ab, the original function value at the point that it's going to be tangent at. Plus, up here, plus the derivative times x minus a. The derivative times how far are you away from a. Down here, we don't have just the derivative. We have two separate partial derivatives. We need to do the x partial derivative times how far you are away from how far your x coordinate is away from a. But then you also have to add on the y partial derivative times how far y is away from b here. And so we can also write down the linearization. So here's how the book expresses everything, the definition of linearization. The linearization of function f of x, y at the point x naught, y naught, where f is differentiable, we have to have all these conditions here, is the function L of x, y is equal to f of x naught, y naught, the original function value, plus the x partial derivative evaluate x naught, y naught times x minus x naught, plus the y partial derivative evaluate x naught, y naught times y minus y naught. And then this gives you the standard linear approximation of f at x naught comma y naught. Okay, so this is linearization of our function here. This is the version that we can plug in values x and y to get estimates approximations down here. Of course, so we just replace L of xy with z. L of xy with z, we end up getting exactly the equation of the tangent plane. Okay, so let's do an example of this. Let me pause through somewhere in here is my example that I have written up. I'm going to pause the video and pick up next video with an example.